Yeah, I don't know why it does it sometimes and not other times. All right, so since I've already done that, this goes with technique number 2. So presumably you've already worked through it. As for the group, you want me to do technique 1 or 3?
1.
All right. Perfectly elastic, so I have this right here, so I have 28. My initial momentum is going to be equal to final. Afterwards, I'm going to say that this is traveling at speed c, and this will travel at speed d, or velocity c and velocity d. This is after. Just because I don't want to deal with the subscripts. So that'd be 7c plus 11d. Unlike the time I was doing this before, I have not defined d as any particular unit, so there's no conflict there. Because it's perfectly elastic, kinetic energy is conserved. So I got 1/2 times 7 times 4 squared plus 1/2 times 11 times 0 squared is equal to 1/2 times 7 times c squared plus 1/2 times 11 times d squared. So it's just conservation of momentum, conservation of kinetic energy. That's 56. So 16, yeah. So I get 56 equals 3.5 c squared plus 5.5 d squared. Just simplify the second equation. 2 equations, 2 unknowns. We could, in theory, solve for c or d in the second equation and plug that into the first equation, but I don't think that's the most efficient. But as with any of these, the most efficient way is the way your mind is working at that time. So I'm going to solve for c in the first equation. So I got 28 minus 11d is equal to 7c. So c is 28 divided by 7 minus 11 sevenths d. We plug that into the second equation, so I have 56 is equal to 3.5 4 minus 11 sevenths d squared, because that's c, just plug it in for c, plus 5.5 d squared. Got a binomial we're squaring, so that's 56 is equal to equals 3.5 times 16 minus 88 sevenths d plus 121 49ths d squared. Now, if I weren't doing those on the board, I probably would have come up with these decimals at some point, but that's probably as good time as any to do decimals. We distribute the 3.5. So 3.5 times 16?
56.
Is it 76?
56.
56. And then 3.5 times
44. Is that at 49?
That's 121 over 49.
8.643.
Say it again.
8.643.
Now, conveniently, the constant term goes away. So what we're left with is 0 is equal to that. (14.143 d squared) minus 44d. You could use Pythagorean theorem if you're inspired, or you could just factor it. So it's d times 14.143 d minus 44. So d equals 0, or d equals 44 over 14.143, which is some magical number someone will reveal.
3.1 repeated.
Meters per second. Now, fortunately, one of our answers is the non-collision solution. So D originally, or the 11 kilogram mass was originally not moving, it was at rest. So we've done something right. And so now to find C, it's just a matter of plugging into here. So it's 4 minus 11 sevenths times 3.1 repeating. And we get
Negative 0.8
negative 0.8
repeated.
meters per second. So that's the final velocity for the 7 kilogram mass and the final velocity for the 8 kilogram mass. Or 11, as people say today. Questions? All right. Number 5. I got a mass sliding at 6 meters per second along a frictionless floor towards an ideal massless spring. The spring I give you the spring constant. The mass hits the spring and they stick together without any loss of energy. How much will the spring compress? What is the period of the spring with the mass attached? How long will it take the mass to stop for the first time? And once it hits the spring, and when it stops, what's the magnitude of the acceleration of the mass? These type problems, there's 2 different approaches we could take, but we'll pick one. All right, 12 kilograms, 6 meters per second. So we'll draw the picture. All right, so what's the approach?
Energy.
Yes. There's no change in the vertical. There's no change in vertical, so even though there is a gravitational force acting on it, it does have a weight. It's moving perpendicular to that, and so therefore it is not doing any work. The spring, on the other hand, this ideal spring, is going to be doing work, but it's a conservative work, so energy is conserved. Again, force diagram here, there will be normal force down. Try that one again, weight acting down, normal force acting up, and then at some point there will be some spring force acting to the left. These don't do work, that's conservative. What's the formula for kinetic energy?
1/2 mc squared.
slightly out of sync, or perhaps you were doing rounds. The formula for potential energy,
Which one?
the one associated with this ideal spring.
1/2 K delta X squared.
All right, so what can we get rid of? What's 0?
The initial spring, initial displacement.
Okay. Mass hasn't hit it yet, it hasn't compressed.
Final velocity.
That's maximum compression, it has to stop. So it is simplified down to the kinetic energy at the beginning is equal to the potential energy at the end. I can get rid of the 1/2, and I'm left with mvi squared is equal to k delta x final squared. And what's finding? Yeah, the maximum compression. So delta x is equal to m over k square root, that's vi. And the mass was 12 kilograms, k was 45 newtons per meter, and vi was 6 meters per second.
Could you move that gray thing?
This?
Yes, please. Just can't see.
That's 45, if I recall correctly. Yes.
It's just right. It's 3.098.
Say it again?
3.098 meters.
Are you saying that's times 6?
Yes.
And that's meters per second?
That's 6 meters per second. That is the initial speed. So now it's crashed into it, it's stuck to it. We now have a simple harmonic motion problem. Define the period. Probably the simplest way is if you know the formula.
So we're working on B now, right?
Yes. Yes. What's the formula for the period?
2 pi square root of K over, m over K.
If you're sort of stuck trying to remember which one is it, m over k or k over m, the bigger the mass, the harder it is to get it to change. So that's going to extend the period. It's going to take it longer to make it oscillate back and forth. So bigger m, bigger period. And also k is a spring constant. The bigger k is, the more that spring is going to try to get back to equilibrium. So as k increases, that should decrease how long it takes because the spring is going to exert more force. So m over k. So that becomes 2 pi times the square root of 12 over 45. Which should be slightly bigger than that, just different units.
3.24 seconds.
If we assume, so let's set equilibrium to be x is equal to 0. We'll make that the positive direction. Which trig function would be, if I wanted to express this as a formula, which trig function would make the most sense?
Cosine?
Why?
Because it's starting completely extended.
If-
Function.
If it started, we're talking about,
Start negative. Wait, never mind.
Yeah, it's implied in part C that we are starting the time as soon as it hits. I did not write it explicitly here, but if time is equal to 0 when it hits the spring to start with, it's not starting at maximum compression.
So does it start in the middle of it?
Pardon?
We use sign when it starts like after it's already started to compress.
Or you use sign when it's at 0 when time to start is at 0.
When it isn't at 0, when displacement isn't 0.
At time is equal to 0, if it's at a maximum, cosine. If it's at 0, sine. You actually don't need to know this to solve this problem, but that's just a different way of looking at it.
So it'd be sign for the time?
A sine would be more convenient. So x is equal to 3.098 meters, that's the maximum, that's gonna be my amplitude, times the sine of,
Is this for C? Or we still will be?
we're, B, that's the answer to B right there.
Okay. Alright, I got you.
Omega, my angular frequency, is the square root of k over m, which is the square root of 45 over 12, which is 1.9-ish.
Yes.
So 1.9 radians per second times time. All right, so I know it's gonna take 3.24 seconds to go all the way, it's gonna hit 3.24 seconds for it to come back to its starting point, the middle. Back to the starting point, heading in the same direction. How long is it gonna take for the mass to stop for the first time? Once it hits the spring.
Our period divided by 2?
Half the period, it's, so if it starts in the middle, half the period, you put it back in the middle,
Oh, a fourth of the period?
fourth of the period.
Does that say rad over S?
Yes, radians per second.
Yeah, I thought it started at the beginning.
The question is worded, how long will it take the mass to stop the first time once it hits the spring? It hits the spring at this point right here, at 0. It's gonna compress, stop, turn around. So it would be, so a full period is gonna do this and back to here. Half the period, it'll get to there, quarter of the period, just partway.
So was that X equals 3.098, was that for C, or was that just another way to do
That
it?
was answer to A.
No, I'm talking about up there.
Oh, that's just that's the formula.
Oh, okay.
This was not required for this question.
Okay. So I didn't get it.
However, if my position is defined by 3.098 meters, sine of 1.9 radians per second times time, my velocity would be 3.098 meters times 1.9 radians per second. Cosine, 1.9 radians per second times.
So now were we working on the C? I just wanna make sure I know where to write what.
Yeah, I'm gonna use this to solve for C a different way. Say it again?
5.8862.
5.8862
Yes.
units.
Meters. It's amplitude. Meters per second.
Yeah, meters per second. I have meters times radians per second. the radians disappear because they're inconvenient, meters per second, times the cosine of 1.9 radians per second times time. All right, to figure out what time it stops, in other words, when v is 0, I need to basically solve for when that is equal to 0. So 1.9t, cosine of 1.9t equals 0. Or 1.9t is equal to the arc cosine of 0. And what's the arc cosine of 0?
1.572.
What'd you say?
1.572.
Okay, pi over 2. So 1.9t is equal to pi over 2, or 1.57 something. 571. So the time when it stops the first time would be 1.571 divided by 1.9, which should be 0.81. So we got some rounding issues there. Which is, it's a quarter of this.
I got 0.826.
You had 0.826.
26.
I'm assuming the 1.9 was rounded off. Okay, so that's rounded off, the 1.571's rounded off, so that's why we're off. And then the final question is, when it stops, what's the acceleration? Again, there are two approaches. I know F equals ma. When it stops, I'm at my maximum force, so it's k delta x is equal to mass times acceleration.